Hello and welcome to our today's webinar regarding the topic Live Analysis of Production Data. My name is Sarah Muche and I'm very pleased to welcome again so many of you to our today's webinar. I welcome very warmly live in our studio Andreas Kühne and Patrick Kaiser. Dr. Kühne is working at Analyses GmbH as lead data scientist. Mr. Kaiser is also a data scientist and part of the software development and IoT team of EMAG. Another guest is Mike Rose, sales director of EMAG IoT and directly connected to us to the studio today. They will guide us through the webinar. We will give you also the possibility to ask your questions during the presentation. Please use for that the webinar tool. And there will be also the possibility to discuss your questions with our experts at the end of the webinar. Today we ask ourselves, collecting production data. And now what? We will give you the answer how to generate with IoT solutions a real added value. Due to interlinking of machines with Industry 4.0 or IoT, there's a huge amount of data produced and saved. But only by analyzing this data, e.g. with EMAG IoT solutions, you're able to identify potentials for optimization. This is what we want to show you today. Maybe we talk about the topic today, which addresses most of all specialists behind programming. For that, I want to do some internal advertising, because next week we have a webinar which presents the EMAG IoT world from our production side directly at a machine. Here you can see more details. I'm very happy to see all of you and welcome you again next week. Today our experts will even start a live analysis at machine and sensory data and show you how fast hypotheses and optimizations can be generated for your production. So far from my side, and now I directly hand over to Mike and wish an interesting webinar.
Yeah, hi, good morning for everybody here in North America, and good afternoon to my colleagues in Germany. Real quickly, you know, when I walk the shop floor, excuse me, I usually hear about OEE and spindle utilization. Sometimes it's good, sometimes it's bad, but obviously the greater the spindle utilization, the higher the OEE rate, the more competitive and usually more profitable an organization can become and usually is. You know, today Patrick and Andreas will speak of how to generate real value based on two case scenarios. But I also ask you to question yourself regarding maybe the analysis of predictive maintenance in lieu of preventive maintenance, predictive quality, tool life cycle optimization, production forecasting, and lastly, improving throughput and yield in regards to data analysis. And now I will turn it over to my German colleagues.
Yeah, thank you, Mike. So welcome to our webinar on live analysis of production data, how to make the best out of the collected data to enhance your production processes. Before we start, some introductory words. Nowadays, it is often the case that the potential of modern production facilities has almost reached its limits. Nevertheless, there is still optimization potential available, for example, due to unexpected machine or tool breakdowns, unobserved quality problems, or inefficient production processes. Today, by means of digital technologies, and here especially by the emergence of IoT, we gain access to machine and production data at any time in the process. By using data analytics, we can get valuable insights into this data and can derive measures suited to fully utilize the production potential and to gain a competitive advantage. So for the first topic, I will now hand over to my colleague Andreas.
Thank you, Patrick. So yeah, what the title already says, today we are talking about data analysis in production. And before we start into this topic, we want to separate what kind of data analysis is there in production. So we separate it in 3 parts. So you can see one of the parts is obviously directly live monitoring of production status and processes. So this is like you monitor obviously KPIs such as OEE, the piece count in your current shift or the cycle times, and to keep the production process transparent. But there are also other things like predictive quality, what we've heard before, like you can monitor the quality of your produced parts and maybe even alert your workers when there are some problems. The topic which we will focus on today is the second part. It's more the analysis of historic machine data. And this often is used to give you some transparency about your production process. You can relate how your production process works, how individual machines are interconnected, and thereby maybe diagnose some problems that you have in your production line, or also identify bottlenecks and thereby optimization potential. And this is a very powerful tool for that. The last part is like the forecasting and planning, and this is like the more you know about your production line, the better you can forecast and plan the events you have to take. This could be simple forecast like the worker when the worker have to make tool changes or like refill the parts in like the automation system, but it could be also more complex things like predictive maintenance or preventive maintenance, which everybody wants to achieve to really reduce unplanned downtimes. Before we can start with the data analysis, we need to have some background in what's there and what is needed to really, for example, collect the data. And here we want to give you an overview of the EMAG IoT products from the Aetna portfolio that are there and really support you in your data collection and also data analysis already with some certain application and services. What you can see on the left are the Aetna IoT Core and the Aetna Cortex. So this is an IPC IoT gateway with a data collection software that is running directly on your machine. I mean, we will get to that in a minute, but we also have some certain application and services such as the Aetna Lifeline dashboards and data apps. So these are little applications that make calculate directly live in production some KPIs and make some little forecast that you really can visualize with these dashboards directly in your shop floor, so that you get a transparency on your production process and see if it runs smooth or not. The last one is the Aetna Health Check and the Neuron 3DG. This is like a condition monitoring / predictive maintenance service. The Neuron 3DG is this little acceleration sensor that you see there on the bottom. And of this one, we will analyze also some data. And this health check service is like a service for condition monitoring where we analyze the machine health. Now we want to dig deeper first on one of the major parts that is needed for data analysis, and this is the Aetna IoT Core and the Aetna Cortex. As I mentioned before, the Aetna IoT Core is like an IPC which is can be directly installed in your machine. On this IPC, the software Aetna Cortex is installed. Aetna Cortex directly gets data from your machine control units such as Fanuc systems or Siemens systems, can also get data from external sensors like acceleration, temperature sensors, but also you can add your data from different APIs such as MQTT or REST API, or even import data from other data sources via CSV sheets. In the Aetna Cortex is a database included with the ring buffer system, so the data is collected until a certain time. When the buffer is full, the data gets archived, so nothing gets thrown away, and so the system is running in a regular manner. But the Aetna Cortex and the IPC is not only running on the machine, it also can run on a higher level, which we will see in just the two slides from here. So that where all the data gets collected of all machines for long-term storage. So I think here I see we have a question.
Maybe. We have already the first question. Yes, thanks for interrupting. And already 2 questions. Maybe the second one for Mike. Is this a ready-to-use solution, and who can I contact for more information?
Yeah, good question. So yes, both of these products and also the products we saw on the previous slide, so also the Lifeline dashboards and the Health Check are ready-to-use solutions. So they are optional for new machines but also available for retrofit. There it depends on the how old the machine is, if it can be connected easily or a bit more complicated. But yeah, best to contact your contact person. Maybe Mike, you can have some words on that. Yeah.
Well, yeah, for North America, the direct contact person would be Jeff DeBoard, our aftermarket and service director here in North America. If you reach out to Jeff, he can pull a machine serial number, take a look at the age of the machine, and then come up with a plan of action to provide you with live analysis and machine monitoring, or whatever else you may require in regards to data analysis.
Okay, great, thanks for this information. So to get back to our presentation, what we have now with the Aetna Cortex is all the data. It's the tool to collect your data from the machines and external sensors. Obviously, if you have data collected, the next step would be the analysis of the data, and this you could do with several different tools. You can just use some standard data visualization tools such as Grafana, or you can even use Microsoft Excel, for example, which almost everyone knows, to do some simple calculations and visualizations. But often people or companies hire now data analysts, data scientists to do a bit more complicated stuff with programming languages like Python. What we did here with EMAG is we developed the Aetna Data Science Pipeline, which is a data analysis environment, in particular for the production environment. Yes, the Aetna Data Science Pipeline has standardized modules for example, to data import, data pre-processing, feature generating, modeling, and model management, and also standardized interfaces, for example, to the Aetna Cortex. And this makes, for example, data import and data storing very easily and smoothly. So you don't have to you have to program the whole interface. You just have to parameterize standard module. But you don't only have to use standardized modules, you can also implement custom modules for your use case and plug it in the pipeline ready to use. And so you benefit from both the standard modules, which makes it very fast for implementation, but still you can integrate your customized modules. What is also very interesting about this data science pipeline, that is really made for production, so it also handles information of machines, like machine IDs, machine types of the line, and also models, for example, can integrate this machine. So you can have a model that is running only on a certain machine type and another model only on another machine type. And the pipeline directly handles which data goes to which model depending on machine and machine type. And this is really helpful. A question that we often get asked by data scientists or data analysts is, can we use data science libraries or artificial intelligence libraries that are standard, like scikit-learn or Keras or something like this? And the answer is yes, it's very easily integratable within our pipeline structure, so you can use all the toolboxes you know and still benefit from the pipeline and have a very fast implementation for analysis of production data. We have certain benefits, obviously, if you use this, since you only focus on the data implementing the use case or the business logic of your use case. We are very fast in development, so a lot of software engineering you don't have to do. And obviously also, since the modules are quite standardized and the interfaces are standardized, they have a higher quality of code. And so you don't have to care much about bug fixing. And obviously, as last point, you are also very fast in operationalization. So you're very fast from developing something in your office or lab and trying something out. You can be very fast in putting it on the machine and being live implemented in your production process. Yes.
We have already another question from our customer. One of our customers says they don't have anyone in the office who is specialized in data analysis, and can this be understood and used by anyone?
Yeah, good question. Actually, in the beginning, this data science pipeline was designed for specialists, like for programmers, for data scientists, for AI engineers. But now we've realized that it can also be easily used by domain experts. The way would be how we would approach this would be a bit different. So if domain experts want to do some more advanced analysis on a regular basis, for example, there could be a way that we write, for example, little scripts where we implement some function and let the domain expert do the parameterization dynamically so that he can benefit. And like this, we already had a case with a customer where we had worked with the head of production who wanted to do some particular analysis in a repeated manner, and this worked pretty well. So he could use it, he could benefit from it, and improve his production process. So yes, in the end, yes. We have now the data collected by the Aetna Cortex, and we also have our analysis environment. And with this as background set, we can now look how this look in practice. How this could look in practice. What we could see here is like something we implemented at the customer side. So you see here a production line with 7 different machines, and on each of these machines, the Aetna Cortex is running. The Aetna Cortex collects the machine data from the control unit and also from the acceleration sensor, and pushes this data to the edge cloud, which is on the customer side. So it's not a cloud in the internet; it's like a server or virtual machine on the customer side, so that the data is not going outside the customers. The Aetna Cortex on the edge cloud then collects the data of all of these machines for long-time storage. On this virtual machine, also the data science pipeline apps are running and perform different data analysis. So they get the data from the Cortex, they do some analysis, store the results back in the Aetna Cortex, who then again publishes the results via MQTT, what you can see here. And then, for example, these results can be shown on dashboards directly on the shop floor and make your production process transparent. So this is something which we regularly implement, and this is a typical data analysis environment in production that we have. With this as background information, we want to go now into our use cases. And today we want to show you 2 different use cases where we think it exemplifies how to use machine or sensory data to generate added real value in production. First, we want to talk about acceleration data from an external sensor that we use regularly to monitor machine health and identify problems. And in the second part, we talk about how to use production data to calculate, for example, takt times or perform root cause analysis.
Is there also a plan to support OPC UA instead of addition to MQTT?
Very good question. Yes, this is currently under development. I don't know the exact status, but I think it should be soon available. So OPC UA is also an interface that we are looking to offer. So it will be available I guess in a couple of weeks. But best contact your Mike or his colleague, yes, for details. Perfect. Okay, with this we can hand over to Patrick, who now goes to the first use case.
Thank you, Andreas. So I will now go on with our first live demo, analyzing acceleration data gathered by our Aetna Neuron 3D sensors. For this use case, we will take a look at acceleration data recorded at the EMAG Turing machine over time. We will visualize and analyze this time series data in a time domain and frequency domain to get valuable insights and detect possible machine problems. For our analysis, we will use Python as programming language. Python will help us to visualize and analyze our data in a quick and easy manner. So before we start, maybe some background information, how we use this acceleration data in our solution Aetna Health Check. Here we record acceleration data regularly and automatically, for example, once a day during a lunch break. Then we have the health check process where an algorithm assesses the machine condition, or how we call it health condition in terms of machine wear. And finally, we can visualize the machine health in a line chart to detect possible trends over time. For this, the measurement is subdivided into different parts, where each part represents an individual test regarding one of the machine axes. For example, you can see here the feed test in X direction, the feed test in Z direction, a spindle test, and a circle test, for example. And each of these tests is analyzed individually by our algorithm. So I will now switch to my programming environment. As I already mentioned, the following live demo, we will learn how to visualize and analyze example acceleration data from our Aetna Neuron 3D sensor, which were collected by our data collector Aetna Cortex. Specifically, we will focus on detecting so-called interference frequencies, but more on this in a second. So the first step of every analysis would be to import relevant modules. Here we only use standard Python modules, which are freely available on the internet. We have modules for data manipulation, modules for data filtering, and of course for data visualization. I will now import these modules. The next step would be to import our acceleration data. Here we have our acceleration data in a CSV file, and we can import this and get a first glimpse of the data. So now here we can see the first 10 values of our acceleration data in X, Y, and Z direction regarding our machine axis, as I already mentioned beforehand. So before we can start our analysis and visualization of our data, we first have to define our sampling frequency, which we got from the sensors data sheet. And now we can plot our raw measurement, our acceleration data package. So now here you can see the acceleration data measurement, and here you can see these single subtests which I already mentioned. And we can clearly see here some dominant part or a noisy part in our data, which we investigate further now. So to get a more detailed look on our data, we can use a so-called short-time Fourier transform function, which allows us to plot our relevant frequencies over time. For this, we created a little function. I will now use the data to plot this in frequency domain. Now we can see here there is some dominant frequency in our data around 500 Hertz, which we refer to as our interference frequency. Now we can go deeper into into analyzing our data. For this, we can take a look at a single time step in terms of the frequencies. For this, I will use the output of our short-time Fourier transform function. And now I can plot a bar graph where we can see the frequency amplitudes or intensities over the frequencies. And here we can see our dominant frequency or interference frequency. And even more clearly here in this plot. Now, this information regarding interference frequency could possibly point out a problem with our machine, for example, with a resonating frequency, damaged rotating equipment, or even a problem with our access drive. But more on this in a minute. What we can do now is we can filter our interference frequency. For this, we have to use a bandstop filter, because as we can see here, there's not only one single interference frequency, but rather frequency band. And we can set the limits here for this frequency band which we want to filter. And then we use a so-called Butterworth filter to filter the data. That's what I'm doing now. Then we can plot our data again.
Excuse me, Patrick.
Yes?
How do you determine the interference frequency? And how may it be different for different machine tools and or different environments?
So we determine the frequency. So we have these. We have our acceleration data, which records our which records the spindle condition, and what we do here. So we are monitoring the spindle motor controller. We're looking, is there a dominant frequency in this signal, and then we can use this information for further further investigation. We can use this for our VL EMAG machines.
Okay, thank you.
We have filtered our interference frequency, and then we can plot our data again and see we've filtered this interference frequency. The interference frequency is gone, and now we can compare the measurement data before and after the bandstop filtering. We can see the clearly difference between our raw measurement data and our filtered data, and so we've successfully filtered our data. Now we can conclude that time series transformation between time domain and frequency domain are standardized functions in Python. You don't need to buy additional modules for this kind of analysis. Visualizing the data needs some extra effort, as we have seen, so we had to create a short-time Fourier transform plot function to identify this interference frequency. But if you have such a kind of useful plot, then it's no big deal to detect such anomalies. With some extra effort, we can automate all these steps. This is already realized in our solution at the health check. And of course, we can use all this information to get valuable insights in potential problems with our machine. And we also use this kind of interference frequency filtering for our algorithm for further tasks. For example, we have some sort of automated segmentation where the algorithm segmentates our acceleration data or our measurement and analyzes individual parts. And for this, we need filtered data to get the best result. So now we've learned a few things about analyzing acceleration data, but how can we use this knowledge for our machines? Well, as we have shown, there is, for this specific use case, we have an interference frequency around 500 Hertz, and one can use this information now to generate recommendations regarding the affected machine. For example, in this specific case, the recommendation would sound like optimize your spindle motor controller by using these detected interference frequency band in order to reduce the vibrations. This may result in an increased part lifetime, for example, of the spindle bearing or the guidances, and could also increase the workpiece quality, for example, the drilling accuracy. And as we can see here, or as I've already shown in our live demo, after the spindle optimization, the interference frequency disappeared. And to conclude, such proactive actions make early detection of problems possible in order to prevent quality issues or malfunctions of the machine. If you're now interested in getting recommendations from our EMAG experts, we already have a ready-to-use solution available, our Aetna Health Check, as Andreas already introduced. We use Health Check, or Health Check offers the possibility for automatic condition monitoring and predictive maintenance. Will help you in detecting such problems as, for example, the interference frequency, as I've shown already. And if you're interested in such kind of problem detection or automatic condition monitoring, you can simply contact us. Okay,
this
so
is great because it takes the responsibility away from the maintenance department or even the operator, and puts it in the hand of the machine and the control system.
So is this a question or?
No, just a statement.
Okay, yes, of course, but you have to have a expert looking at the data. So when we use this for automatic condition monitoring, and we want to go deeper into diagnosis, for example, we can still rely on the EMAG experts, for example, to help us detecting the problem or component of the machine which is affected.
But I have another question from our audience regarding the frequency analysis tool which has been mentioned. Is it possible to use it for different or additional problems with the machine? And some more examples, please.
Yes, of course, you can use such kind of frequency analysis to detect various kinds of problems which are related to some anomalies regarding frequencies or some dominant frequencies. For example, you can use it for roller bearing problems, lubrication problems, loose fasteners or imbalances. Here these some examples, but if you want more information, just contact us and we can look at your specific problem. Then I will hand over to Andreas, who will tell you something about calculating takt times and performing a so-called root cause analysis.
Yep. Thank you, Patrick, for handing over. Yeah, in the use case Patrick showed, we talked about sensory data. Now we really focus on the data that you can get from your control unit or from a machine control unit. And because we think this data is already very information rich, and it can be used to do different, like to really monitor and also analyze the production process already by calculating different KPIs such as OEE or piece quantity. But you also can do way more complex things. And what we want to show you today is like get a bit of taste of what you could do. So first we calculate more simpler tasks, just calculate the takt times for all the machines in the production line. But also we want to get you a taste what you could do if you relate different information that you collect with your Etna Cortex. For example, if you relate system messages and takt times to do a root cause analysis. And with this, I will switch to the demo again. And I hope in a couple of seconds it should be live on your screen as well. Perfect. So the demo is now split up in two parts. In the first part we do the more simple task, calculate takt times, and in the second part we will do the root cause analysis. For the demo we will do with Etna Cortex as a database in the background, and also with the Etna data science pipeline. But like in the last use case, before we do the analysis, we have to set up and configure the Etna data science pipeline. So we need some configuration, for example, with authentication details, and also details where the REST API of the Etna Cortex is hosted, and also of how to map the data that is lying in the database could be mapped to objects, data objects that are in the data science pipeline. So there is some configuration on this side. On top, I mentioned it already before, the Etna data science pipeline takes also into account information on your assets, meaning on your production setup. For example, we give information about which machines are in the production line, how are they organized in operational units, how are they organized in different lines, or even at different locations. And this information can be used in different modules of the data science pipeline, for example, for data loading, aggregation, but also for modeling. And what you can see now here in the code, this is where we perform all this task. It already started. Here we get the details from the Etna Cortex authentication. Here we load the asset hierarchy key. So in this case, we just have it in a JSON file stored. And then in this part, we define the mapping rules. And we see the MongoDB connection was set up correctly. So we can move on to the next part. So after parameterization, what we do now is we want to load the data from the Etna Cortex and do some basic pre-processing. So for loading of the data, we can use a standardized module, the raw data loader, and we just have to parameterize it. So we have to tell it the value types. In this case, it's the runs completed, which is the workpiece counter, and we want to load the system messages that are coming from the control unit. We also tell it from which to which time the data should be loaded. So in this case, we have data from the 2019, the 2nd of October, from 1 p.m. to 3 p.m. So it's just a little time window for this example case. What we also do is we define the machine IDs. This I already did on top, so it's all the machines in the line, and also the Etna Cortex authentication. Then we parameterize here in this part the module. We add it to the pipeline again, add some more pre-processing. I don't want to get into this. I'll show you the results. It's easier for you, I think, in the end to understand what happened. And let it run. What you can see now here is the log which comes out of the data science pipeline, and here in this detail you see that 6 data objects were loaded from the database, and each of these data objects refers to a data set from one machine of these 2 hours. We can have a look at one of the data sets of the machine. Of one machine. So it's like now for the machine 109543. We have now at the index, we have a timestamp where, for example, the work pieces were generated, and one of the columns are the system messages. So at these times there were no system messages, but there were a lot of runs that were completed. So the workpiece counter is going up continuously. Now the question is, what can we do with this raw data? We said, okay, now we want to start calculating takt times. And the most simple way to calculate takt times from such information is just to take the time difference between the production of two different work pieces. And this is what you can see in this little schematic and what we're going to do in the next step. So we get the data from one machine. So this is what we do here. We calculate the difference between the timestamp indices and transform it into seconds. And the result is what you see here. So now we have for each completed run the time of the production times or the takt time of each work piece. And you can see for most work pieces we are around 87, 88 seconds for the production time, but there are already some slight outliers. Obviously we can also just visualize it, which is way easier for human beings to understand, to just see the data in like a linear line plot. So what you have now here on the x-axis is like the time, and on the y-axis is like the takt time of each work piece. And you see for most work pieces we have a constant takt time around 80, 87, 88 seconds, with some certain outliers which are around 100 or 106 seconds, which we know it's due to the measurement system. When the measurement is active for a part, then it takes a bit longer for the production, which makes sense. But there are also some larger outliers. For example, here 300 seconds or even 320 seconds. So there something happened obviously in the production process. It did not run smoothly, and it's interesting what happened here. What I showed you there was a calculation of takt times only for one machine by hand. So I did it manually. When we now use this the ETNA data science pipeline, one of the advantages you have, you can just generate, for example, a feature generator that calculates the takt time. Quick recap. I showed you how to calculate it for one machine. In the next step, we want to calculate it now for all machines in parallel. And this is where the data science pipeline helps you a lot. So what we do, we define a module called the takt time feature generator, in German Taktzeit, that's why the name, and let it run all the data objects. So we have a data object for each machine. And now as a result, we get takt times for each machine. So this is what I'm doing in the next step. I just add this module called takt time feature generator. Let it run through and get different takt times as a result. Yes, so now I have the takt times. Obviously, I also want to see how are the takt times distributed among the different machines. This is what I do in the next plot. What you can see now here is like this takt time distributions for 6 different machines. So all of these little parts are the different machines. And what you see here are the takt time distributions of the 6 different machines. So on the x-axis again the takt times, and on the y-axis now we have the frequency, so it's a histogram plot. And you see for almost all machines, most of the time we have the good takt times of about 90 seconds. But obviously there are a lot of machines where we have some outliers above, let's say around 120 seconds. So like here I would separate it, and what we want to do in the next part is we want to identify system messages that relate to these outliers. And for this, we first have to flag these outliers. And this we can also do with this takt time feature generator. We set a threshold of 120 seconds. Add this here to the feature generator, let it run. And as a result, you see now we have not only the takt time for each individual produced workpiece, we also have a flag calling this is an outlier or not. So everything above 120 seconds is marked as an outlier. Okay, and this you can also visualize. You can now use this flag to separate your takt times of each workpiece into 2 data sets. In blue now all the takt times which are good production or good takt times. In orange are the takt times which are outliers. And this helps you already to get transparency of your production process and see what's going on. So now we are at the end of the first part. We know now how to calculate takt times. It's a quite simple task, but it could help you to get transparency in your production process. And now we want to move on to a bit more complex task. Now we want to relate system messages to takt time outliers, and this is what we do next. First of all, we're going to explore the system messages. So I have to already excuse me that the text is now in German, but it's like the data is from a German machine, so with a German control unit, and so it's already stored with German text. But what you see here is like about 24 different warning and info messages that are collected from the machine. It says, for example, that the worker is at the machine and the front door is open, or that the automation system is not working properly. But you can see that a lot of different things are ongoing in these 2 hours of production, which is quite interesting. To now perform this root cause analysis, we have to do 2 different steps. In the first steps, we have to relate if a system message was active when a workpiece was produced. So if it could be directly related to long takt times. For this, we have a look at how long was a system message active when a workpiece was produced. For example, the system message 2 in this example was produced in this outlier, in this orange one, and also in this other outlier for a long time. So it seems like it could be like if out of intuition you could think, okay, this could be related. And this we want to teach let the algorithm learn if messages are related or not. So what we are doing, we calculate relative times of a system message when it was active during the production of one workpiece. And this is like a feature matrix that we get out of this. It's like really way more technical and more to the tech-heavy people, I guess, of you. But don't get scared. It's not much information. The thing you have to take away with this, we take this information, was a system message active when a part was produced, and the information if a part was an outlier, put it into a machine learning model. In this case, we use a decision tree model. This learns the dependency between these two features and target variables, and gives us in the end some kind of dependency. So in this case, how does system message influence long takt times? This is what's happening in this pre-processing step. We calculate the relative time of a system message if in the production of a workpiece. Here I really don't want to go into the details because it would, we would run out of time easily. But we see it's all running through. So now we have all these features, and now we want to train this machine learning model, like I showed in the schematic on top. So what we do here, we define what kind of models do we want to use. This is now a decision tree model of a decision tree classifier. One of the libraries I mentioned before is from scikit-learn. We define the machine IDs we want to add in, and also like what are the features with all the the system messages that we have, and also our target variable. We add this to the pipeline and train this module, and we see it's went through. And now what we can do, we have a look at the model structure and how the system messages are related to the targets. And this is like a very typical plot you can get out of it. It's kind of called a feature important plots. And this tells us how important is one, in this case, a system message for takt time outliers. And what we can see here, like the top message was Warte auf Wechselschnittstelle 1 in German. It means like that the machine is waiting for the automation system to pick up a produced part and bring it to the next machine, or to bring a raw part for production. So meaning it's not a problem of the machine, it's a problem of the automation system and their outliers, which is kind of interesting for further to see where there's optimization potential. And like this, you could use such simple data like production data from control units to really analyze your data and identify bottlenecks and optimization potential. With this, we are at the end of our demo. You can switch back to our slides. So what I showed you now was like the simple case of calculating takt times, and maybe a bit more complicated case to do some, let's say, relation or root cause analysis. For this KPI analysis, we have some different tools like the Aetna data apps that calculate different data, like for example the takt time monitor, where we calculate takt times and also identify takt time anomalies. We calculate the OEE on different levels, like machine level, operation level, line level. Also, we do some forecasting, like we have a smart tool change app which really forecasts when does the worker need to be at the machine to perform a tool change. So he knows like at 3 p.m. I have to do the tool change at machine 1. He can prepare all the tools, so he's ready. The machine downtime is really reduced to a minimum. And also we have we have to support with transparency about the part quantity that is produced during shift, not only the current produced quantity, but also a forecast. Like you can have a forecast already early in the shift that if you produce in the same production speed like you produce till now, then you will not reach a goal, or you will reach a goal, and you can plan accordingly your day and your shift. And this helps to keep the transparency on the shift, and also to keep up the production process smoothly. Yes.
One more question from our audience. What are possible next steps after dependencies between system messages and takt times have been discovered?
Yeah, it's a good question. I think so it really depends on the context, obviously. So the ideal goal or the ideal scenario would be that out of such an analysis you can have either a diagnosis or you relate a diagnosis where you could do some optimization, or you identify some bottlenecks or some optimization potential. So in the case of the automation system, if this for example occurs also when you analyze the data over a longer period of time, for example a couple of weeks, and you see also automation system seems to be like the main driver of long takt times, then you can think of how to optimize your automation system, for example with buffer bands or with additional machines or like with reprogramming of the automation system. If you have like problems in one particular shift and you do such an analysis, it might help you rather to diagnose the problem. So it gives you transparency of what happened during a shift, and you don't need to rely on the shop floor meeting that people remember or even don't remember because they didn't know what was happening in the machine. So it gives you just the transparency where you can diagnose and relate what you have to do in the next. So it should support you in doing optimization and diagnosis.
Would it be possible to send copies of the materials which you used for the demonstration?
Yeah, sure. So we are happy to hand out the demo materials, so we can send you a PDF afterwards if you're interested. And even if you want to go into deeper details, we know it's a very short period of time. We can have a quick discussion maybe via web. Yeah.
Could it be possible to show the live data screen for cycle time, OEE, etc.? So the question is how it looks like.
Yes. So maybe we can switch back to my screen. So. I cannot provide you with the live data, but maybe with like a recorded live data of a screen. So this is like the Lifeline dashboards, how they are shown. Like it's a demo mode we have because we cannot go to the data of our customers because it's theirs. So what you can see here is like one of the dashboards of the production line. I just stop it here. So you can see here on the left is this tool change option. So there you can see for each operation and each machine when the next tool change is happening, like really with the counter that's going down. So it's really nicely plannable by the worker. So he has transparency about his process and also can plan his breaks accordingly. We have like this takt time, which is like calculated. Here you can see the takt time of this machine was like for the last part was like 43 seconds, and it's like an average 43.7 seconds. And here is the workpiece counter. It seems like in this shift nothing was produced yet, so it's like at no workpieces produced, and we have like we won't have any production till the end of the shift. And here is like the machine status. You can see on the right, where you can see like the current if the machines are currently active or not. Yes, and just jump forward a bit. We have some other screens maybe. Exactly, this is like some other visualization where we see the OEE. Obviously, if nothing is produced, the OEE is at 0, but obviously depends. Here on the top left is also something of the health check we've shown before. Like this is like the machine health of the individual machine parts. So this is how it looks in practice. But to also say it can be customized to your needs. So there's no fixed view. You can have different views on the machine level, operation level, production line level. It all depends. Yes, what are your needs and what information you need in your production. Okay, with this I would say we can switch back to the presentation. As I said, these are already ready-to-use solution. Just contact EMAG to get more details about it and if it would work for you. But obviously, you can also get more into the more complicated analysis. For example, we just calculated before the takt times and did the root cause analysis. But also, you could also use the takt times to understand even more about the interdependencies of the machines in your line, especially if they are connected with the automation system. What you can see here is like another visualization of the takt time. So all the blue colors are workpieces that were produced with a good takt time. In red are workpieces that were produced with that had a very long takt time. And what you can see here, the rows are all the different machines, and you can really see examples where at some machine it's starting to get red, so it has like problems and it's not producing, but this propagates then to different machines and different operations. And this is very interesting because if we even took this analysis a bit further and learned with machine learning models interdependencies between machines, and then you can really forecast and identify bottlenecks in your production line and optimize it. And this is really helpful in practice. with this example, I want to end, and we generally end the live analysis use cases. For the wrap-up, I hand over to Patrick, who gives us some final thoughts.
Yeah, thank you, Andreas. So this brings us almost to the end of our webinar. So here on this slide, we've summarized the 3 key learnings for today. Data from production machines offer a vast amount of unused potential for valuable insight and production optimization. So analyzing your machine data offers possibilities to monitor critical processes, to analyze historic machine data in order to find some optimization potential. And it also allows forecasting and planning of maintenance times and supply chains. And it's important to have a good analytics framework, which helps you to quickly transform your technical and business insights obtained from data analysis into useful analytics solutions. So we are happy if we've attracted your interest, because our EMAG IoT product portfolio will help you in building data analytics solutions specified for your challenges and needs. You simply have to contact us to get more information. Okay, so Mike may have some few words.
Yeah, in closing, we'd just like to thank everybody for taking the time out. We ask you, we want to know what the factory of the future looks like within your organizations. If you're running EMAG, how can we help? How often and when do you look to analyze the data on our machines as well as our competitors or even different processes. So we're here to help, and please know that we're prepared and ready to support you. And as I said earlier, feel free to get a hold of Jeff Gibord, our service director, or feel free to contact your local regional sales manager and or your key account if need be. So again, we thank you, and we look forward to seeing you on future webinars.
Thank you to our experts, and welcome back to our audience also. As I already mentioned at the beginning of the webinar, we will now come to your questions if there are some more. And if there is a question you would like to ask in confidence, you're very welcome to let us know. And then we can arrange a one-to-one appointment after the webinar, and you can contact us by mail freely. We will show you the contact details also. So then I would say we are ready for more questions, and I see there's the next one coming in. For customers with existing machines, what is the requirement for hardware, software for machine monitoring, maybe machine data forecast and planning?
Yeah, I can take it. As a starter, I guess everyone needs kind of to get the data out of the machine, as I mentioned before. So you would need the Aetna IoT core and the Aetna Cortex, which could be installed at your machine and makes you ready to collect the data. And then it depends on what you need. If you need more the transparency and need more the data from the control units, calculate KPIs, identify bottlenecks, and so on. And then I think the Aetna Lifeline dashboards with data apps are really the thing you should go for. If you're interested in predictive maintenance and condition monitoring, then the Aetna Health Check and the Neuron 3DG is the thing you need. So it depends. Contact your EMAG person, and then we figure out the details together, I would say. Yeah.
Are there some more additional examples of data analysis, how machine data can be used?
Yeah, also a good question. That there's a bunch of things you could do to analyze data, and also like a bunch of use cases you could address with data. To just give you a bit more of a taste, what we were doing, like you can bring the KPI analysis to even more details to try to identify anomalies in your KPIs, for example, how the KPIs change during your productions, during your shift or during your weeks. And like this, we already found some bottlenecks in the processes, like which for example, that some shift changes which should had some major impact and resulted in that we had overlapping shifts and improvement, or even like in shift changes, which we had problems. But also the thing Mike said in the beginning, the preventive quality or predictive quality was the thing we addressed in the past. So we had like a customer who had quality problems, and we developed a AI solution based on the Aetna Cortex and the data science pipeline, who directly calculated from machine data if the quality of a part was a good part or was a bad part. And when it was a bad part, then directly the model gave a signal to the control unit, and the control unit put it out of process. And like this, the customer could reduce his manual controlling of the work pieces about 95%. So that had a big benefit. And so like this, there are a bunch of use cases out, all that you can address with data analytics.
As far as I can see, there is no further question from our audience. But here you can see our contact details. So if you want to contact us after the webinar, and then if there are no further questions, I would say we reached the end of our webinar, and I hope you were able to take some interesting pulses with you. And soon you can also find our today's webinar on YouTube, where already other webinars are uploaded from EMAG. And once again, I will give you a short reminder for the webinar next week directly from our workshop. And so far so good. Thanks a lot for your participation, also in the name of our experts, and take care, and if you want to, until the next time, goodbye.